So welcome to the Colloquium today. We have here as our guest speaker Marc Pinsonneault. He did his undergraduate at the University of Texas in Austin, and then did graduate studies at Yale, and also in Yale did a postdoc, and then moved on for a faculty position in Ohio State. And since then he has stayed there and is a full professor at the Ohio State University. So today, Marc is going to talk about the inner lives of stars. So let's welcome him to Heidelberg.
Okay, testing. Okay, first of all, I'd like to thank you very, very much for the invitation to come here and speak. It's a delight to be able to do so, and I also wanted to add that a lot of the work that I'm doing represents the outcome of two very large collaborative efforts, one involving the Sloan Digital Sky Survey and one involving the Kepler Asteroseismology Science Consortium. So there's been a lot of work done by a lot of people whose work I'm going to be discussing here. And there's also three students whom I've worked with who are remarkably talented and who have been responsible for a lot of the new results that I'm also going to be talking about here. This is Courtney Epstein, Jamie Tayar, and Jennifer von Saders. And it's a real privilege to be able to be working with students who are just tremendously talented in an exciting field. Now, I like to sort back here and think about where we're coming from. And some of the most interesting questions in astrophysics are primarily questions of origins. For example, how was our galaxy assembled? How do stars and planets form? How do stars live and die? Where do the elements on the periodic table come from? And we have cooked up over the years a sort of certain standard knowledge about, say, the life cycle of the sun, the life cycle of stars. We've cooked up kind of a generic picture of how we measure the properties of things like stars. And we're so used to the idea that we've done this that we perhaps sometimes don't recognize that there are pretty basic limitations in how this is actually done. So if, for example, we try to measure the ages of stars, we typically will do something like put down a color magnitude diagram, we'll measure the luminosity of the stars, we'll plop some sort of theoretical models on top of that, and then we will read off an age from that thing. But that's not actually an age in the sense that we're measuring the age of the sun, right? We're measuring the radioactive decay of meteorites or the like. We're making indirect inferences, and these indirect inferences have a whole series of embedded assumptions in them. And so if there's a message I want to be bringing here, it's that we now have very new tools in terms of time domain astronomy that lets you measure these things in fundamental and different ways and also provides you with new and additional observables. And so rather than thinking about the classical picture of how you understand what a star is, you should now be thinking that we have a lot of new ways of measuring the properties of stars, including some novel observables of core properties that have always been invisible to us. And I think that there's going to be a lot of consequences that emerge from this. And so if you want to answer these questions, the solution to many of these kinds of origins questions is, of course, galactic archaeology. We like to think of ourselves as being sort of Indiana Jones without the snakes, at least some of us do. In practice, the reality is a little bit less dramatic than that. But nonetheless, we can do things like run these really powerful, remarkably powerful and beautiful large-scale structure simulations. Here you're seeing a slice of the Millennium simulation here. On this side, this is kind of a zoom in and kind of a GMC level scale. And this is kind of a disk galaxy that you're forming in this kind of picture. And so we'd like to be able to take a simulation like this and be able to test the physics that goes into it. These kind of structure calculations are telling us about the time scale for forming the disk of a galaxy, for the time scale for assembling the different particles. And these are things that in principle are very, very well tested or testable in stellar interiors theory. The basic problem here is that basically we're only seeing surface diagnostics. And so as a result, the kind of things that we really, really would like to know, for example, the mass of a star, the age of a star, the distance perhaps to a star, are things that we infer indirectly or at all. And this is also frequently the case that we can only look at these in very, very special systems like star clusters or in binary stars or the like. Now, by contrast, if you go to time domain astronomy, you can actually have some other diagnostics. You have non-radial pulsations. Essentially, all low-mass stars are non-radial oscillators. And you also have available rotation information. I'll only be able to talk about rotation a little bit in this talk, but this is a very, very exciting development in time domain astronomy that gives you a fundamentally new window on the ages and properties of stars, and is also tied to fundamental physics questions like the origin and generation of magnetic fields. Now, the basic principles behind non-radial oscillations kind of can be seen here a little bit in this gorgeous image from the Swedish Solar Telescope. Basically, the outer layers of cool stars are turbulent, and this turbulence generates waves. This is an intrinsic property of any star with a deep convective envelope. And these waves have two different kinds of waves that are produced. One of them is sound waves, or P modes, and one of them is gravity waves, the rough mathematical equivalent of water waves. Now, you have to think of stars as having sort of an 8 order of magnitude density contrast from center to surface, and so as a result, any waves that propagate are going to be refracted. And if you were to follow the trajectory of, say, a sound wave, it would kind of bend down, come back again, and go all the way around. And in this particular case, if you come back to the place where you started, you can have constructive interference. You're going to have a whole series of nodes where specific places on the surface of the star are actually rising and falling. And there's going to be a mapping, which is seen in this beautiful helioseismology data, between the spherical harmonic degree of the modes, the period of oscillation, and the horizontal wavelength, the separation between the nodes, when you can actually get spatially resolved data. And so you zoom in, and these are individual, discrete frequencies that can be mapped out. In the case of the sun, we have about 10 to the 5th of these modes that have been identified. There's perhaps 10 to the 7th modes that are actually excited in the sun. And these are primarily the sound waves out here. Now, there's also G-mode waves, or water waves. These actually can be generated. If you think of turbulence hitting a stable boundary, it hits the upper part of a boundary. The waves propagate through the radiative interior, where they can bounce around, and they're then damped in the convective regions. And so you would therefore think that these G-modes should in some sense be trapped in the inner core, but tend to be damped. So for example, in the sun, we don't actually see G-modes. We do see them in other stars. That's actually an important new discovery from our era of space astrophysics. And so if you were thinking about this, what you would do is you could imagine that each of these modes actually has a different initial bending angle. They're going to propagate to a different region, have a different surface pattern. This is a snapshot in Doppler space, redshift and blueshift, of a particular mode showing kind of the radial and surface dependence of the actual motions, if you could capture something like that. If you want to think about stars, of course, you're not going to get this kind of spatially resolved information, but you can actually get, if I can find my mouse, maybe this is, how do I get to a mouse from here? I get a laser pointer, or I can just cheat and do it this way. Now, if you were looking at the surface of a star, this is what a low-order mode would actually look, with the amplitude greatly enhanced. And so you can see here, this is the bouncing ball, or L of 1, M of 0 mode of oscillation of a star. And so you can imagine that if one side of this star was actually getting colder and another side was actually getting hotter, you would actually see coherent brightness variations with a periodic time scale that corresponds to this motion. And by comparison, if I looked at another mode, I could have a different oscillation mode. This is L of 1, M of 1, and you notice that unlike being up and down, this one's actually side to side. This is an example of some of the clever things that you can do with this seismology. In fact, if you have a rotationally split mode, it turns out that the amplitude of the mode in this direction that's rotationally split is different than the amplitude of the mode that goes up and down, so you can actually solve for the inclination of the star by looking at the amplitudes of the different modes that you see. And so the point is that each of these is going to have a different characteristic frequency because it's sampling a different piece of the structure of the star. This is an L of 3, M of 3 mode. Each one is going to have a different dependence on inclination. If I get enough information, I can start to reconstruct the internal structure of the star by looking at the frequencies of oscillations of these modes, provided that I can measure them and provided that I can characterize them. That's the second important piece, that is, say, understand which mode I'm actually looking at. Now, Kepler, in this case, has been is a alleged planet study mission. I understand that they find planets with this thing, and I'm delighted that they do. In our particular case, from my point of view, they're taking movies of 160,000 stars every 30 minutes And in some cases, they're taking movies of stars every minute. And the movies of the stars have revealed a rich amount of information about the physics inside the star. And so I'm going to be focusing on the results from Kepler because they're so beautiful and we've learned so much from it. Now in stars, we don't actually see the resolved disks, so you only observe the low order modes. And these are some pre-launch simulations of what we expected to see from Kepler for solar-like stars. So train your eye. This is a Fourier transform of what the light curves actually look like. You have this background here of the turbulence, the granulation that you're seeing here. You see the non-radial oscillations, and this is the predicted solar-like pattern that you expect to see. There's a theoretical prediction here that these modes here ought to be evenly spaced between modes of the same spherical harmonic degree L and different radial order N. And so this characteristic very even spacing is clearly seen in the sun. There's an envelope of power where this non-radial oscillation shows up. And the prediction was that the solar-like oscillations ought to be visible for bright stars, say V less than about 11. In this case, we looked at about 2,000 of these. We have about 600 with very, very good data. And the quality of this data is extraordinary. This is not the sun. This is a Kepler target. This is 16 sig A. If I were to put up the solar non-radial oscillation spectrum, it would actually look like this. In fact, this is a little bit better than the low order solar oscillation spectrum. It's absolutely astonishing in terms of quality. You can see that you can measure this exquisite pattern of frequencies that's here. These things are detected as non-radial oscillators. We've tagged them with the frequency spacings, and there's two different things that you can measure here. One of this delta nu, or large frequency spacing, is to measure the mean density of the star. You can also observe that you have these two very, very closely related peaks here, right next to one another, the L of 0 and the L of 2 modes, and the spacing between these two things is actually related to the sound crossing time of the core, which is a measure of the helium content. And so by looking at something like this, I'm actually measuring mean density in one case and the amount of helium that's been burned in the star over its lifetime in the other case. And so you're already getting a rich amount of information. You can also see, by the way, a rotational splitting. If I zoom into one of these peaks even further, I actually see a rotational splitting. And this rotational splitting is actually clearly measured in this case. So there's a rich amount of astrophysical information about the structure and evolution of the stars encoded in this. Now, before I go into any details, one of the things that you notice most immediately are these are just the Fourier transforms of the non-radial oscillation spectrum from 5 stars. This is from a beautiful review article by Bill Chaplin and Andrea Miglio that I'd recommend. That's in astronomy. That's in annual reviews. And when you're looking at these, you see a remarkably strong trend here. This trend is manifest in the amplitude. Notice that this goes up to about 800 as opposed to about 20. You can see that the frequency of maximum power changes enormously. And you can see that the spacing in frequency between the modes is an extremely strong change here. These stars differ only in their surface gravity. And so this is the first thing that you get out of this, is that the surface gravity measured from astroseismology is incredibly, exquisitely measured by this observational set of properties that are correlated. The mean density, the atmospheric cutoff frequency, and all the other pieces. You also will see that the amplitudes are very, very high for evolved stars and very low for unevolved stars, which is going to be important to understand what you can see with this. And so if you looked at this from an interiors point of view, one thing you can do is you can try to study the individual frequencies that I talked about. And there's beautiful games you can play with the microphysics when you're trying to study the individual frequency pattern. But I just showed you a hint that basically I can get very important information about global properties of a star, things like the mass and the radius and the like, by looking at some broad average properties. And so, for example, I can measure the frequency of maximum power, indicated here. I can measure the frequency spacing here, delta nu, and asymptotic theory predicts that this frequency spacing should scale as the square root of the mean density of the star. And this frequency of maximum power appears to have a semi-empirical relationship to the surface gravity. And so if I have two pieces of information and two unknowns, I can then solve separately for the mass and the radius based upon knowledge of the temperature, but I don't need to know anything else about the star to be able to predict the mass. And mass is an incredibly important property for understanding stellar structure and evolution. And so, in effect, we can use this to measure two bulk properties, frequency of maximum power, frequency spacing, and then back out mass, radius, and surface gravity for bulk stellar populations, not for binaries, not for stars in clusters, not for special stars, but for any star you want to. Now this turns out to be a working tool for stellar populations. What I'm showing here is the 600 dwarfs and subgiants with precisely measured HR diagram positions from astroseismology. These are not parallaxes, but they are extremely precise radii inferred from the astroseismic properties. And what I'll be doing is I'll be giving kind of a quick zoom through the spectra, the power series of all of these stars. This is due to Bill Chaplin, who's done a beautiful animation here. And so you can see over here, I'm looking at the more evolved stars. I have a relatively lower frequency solution with a high amplitude. As I move down closer to the main sequence, you know, as the amplitude drops, I start having a higher frequency set of power over here. It moves over here to the dwarfs, where the amplitudes are very, very small and the frequencies are very, very high. I then go back up the main sequence. I can start to see this. By the way, there's also an excess power over here, which is the rotation period of the star. That you can see in these Fourier transforms. And there's a huge amount of information encoded in this, which just, by the way, came from the first month of Kepler data. They had 1 month of short cadence data from which all of these light curves were taken. Now, in terms of giants, the situation with Kepler is different, and there's actually a much more interesting backstory. People knew at some level that the sun was a non-radial oscillator from the helioseismology data. And we knew that if we looked at other stars like the sun carefully enough, we would see non-radial oscillations in them. In the case of red giants, by contrast, there was actually a real theoretical controversy about whether the modes would live long enough to be seen. And so as a result, people were not necessarily expecting that they would be able to find non-radial oscillations in giants. And so Kepler targeted giants not for astroseismology at all. They targeted giants as an astrometric reference grid, and they targeted giants as a way of looking for planets. I don't even know how many planets have been discovered around these giants, but they turned out to be wonderfully astrophysically interesting, because the planet search cadence in Kepler is 30 minutes. So every 30 minutes they snap an image and they look for transits. The characteristic pulsation periods of red giants are days to months. And so as a result, a 30-minute sampling is perfect for measuring non-radial oscillations in giants. And we discovered very, very quickly that all of the giants in the Kepler field are detected high-amplitude non-radial oscillators. This is a huge advantage. There were 14,000 stars monitored. I said 14,000. This number turns out to be a moving target. The actual number that was observed is something closer probably to about 22 to 23,000. Only 14,000 of them we knew were giants. It turns out there's 9,000 more stars that Kepler looked at that were giants and we didn't know it. So there's actually more than that. And the observed frequency pattern is extremely complex. If you want to zoom in, this is a typical red giant. This is a dwarf. You notice the dwarf has this nice, lovely, very, very evenly spaced pattern of excess power from the non-radial oscillations. This is what you would have expected for a dwarf. The giant, this is not noise. These are all detected modes. They're all clumped, they're bunched together, they're very, very complicated, and that turns out to be a sign that there's some really interesting and unexpected physics that gives us a window into the interior of a star. This complicated pattern is explained by mixed modes. The basic idea is in the sun, the P modes have a characteristic frequency of about 5 minutes, the G modes have a characteristic frequency of about 3 hours, okay, so they're not commensurate. In the red giants, the core is contracting, so the density is increasing. The envelope is expanding, the density is dropping. And it turns out that the frequencies become commensurate. And so, in effect, I can see modes of mixed character imprinted at the surface. And if you step back and think about it, this is a remarkable, remarkable thing. We have a core here, which is a proto-white dwarf. Okay, it has a density of 10 to the 5th grams per cc. It's the size of the Earth. There are G modes rattling around in this Earth-sized thing that are visible at the surface of a red giant that can be as large as the orbit of the Earth. Okay, so you can see an Earth-sized thing embedded in a solar system-sized star. And you can clearly see the frequency pattern of that Earth-sized thing imprinted on it. However, there are purely radial modes, L of 0 modes, which are pure P modes. So I have one pattern here, a thicket of lines, which is a pure P mode pattern, and then I have another thicket of lines that has imprinted on it the properties of the core. So I can see the core and I can see the envelope simultaneously in the time series data from these red giants. And comparing the two things basically yields remarkable information about both. What I've done here is something I usually hate doing because seismologists love this diagram and it's hard to explain. It's in a shell diagram. And the basic idea is, but it nonetheless is illuminating in this particular case. The basic idea is as follows. Let's say that I had an evenly spaced set of frequencies here, an evenly spaced set of frequencies. If I plotted up frequency versus frequency modulo the spacing, if everything was perfectly evenly spaced, I would have a perfect vertical line. Then if I had a second set of frequencies that were just offset by an exactly equal amount, I'd have another parallel vertical line next to it. And that would be a sign that I had two patterns that had exactly the same uniform frequency spacing. Okay, and that would be a vertical set of ridge lines in this diagram. And this is a dwarf. This is an example of something that looks more like that. You notice, by the way, that there's a curvature here. This curvature is related to reflection effects that actually occur near the boundary in the atmosphere of the star. Well, that's what's actually causing the curvature here. If I look at a subgiant, you notice that instead of having the perfect vertical lines here, I have these patterns where there's this huge jump. There's modes that just disagree. What's happening here is for this one critical frequency here, the G modes and the P modes are interacting in the star. And so I've hit a case to where these two patterns are now crossing for the first time, and I see one place where they go. That's what this is here. That's a subgiant. Then I go to the red giant branch, and I see that the pattern gets really, really messy because these interactions between the patterns are overlapping more and more and more. And I'm seeing more of that. And then I go to the red clump, and I notice that there's an even more complicated pattern. Well, the difference between these two turns out to be that one of them has a shell hydrogen burning source, and the other one has a core helium burning source. The density of the core is different by 2 orders of magnitude. The frequencies of the G modes are different, and the interaction pattern is different. So in other words, I can tell whether my giant has a shell hydrogen burning source or a shell hydrogen and a core helium burning source just from the frequency pattern without knowing anything about the surface information at all. I can paint it, the core properties, with the non-radial oscillation properties. And this is, again, something that was not anticipated at all. This is actually the real joy of doing astronomy, as you go and you do something, and then you see a pattern you didn't expect, and you're like, wow, this is actually kind of neat. It's kind of nice to be able to see the theory taking you places you didn't know you were going to be able to go. Now, Kepler by itself actually is a photometric mission. And so one of the key pieces that you need here is if you want to be able to do a really, really powerful job, you need to be able to actually combine photometric and spectroscopic information. And so we very quickly realized that we would need spectra, not for 1 or 2 or 3 things, but from my point of view, I wanted spectra of everything. So spectra of about 14,000 giants or so. Spectra of a couple thousand dwarfs. And so we hit upon the idea of combining the apogee, SDSS-3 apogee survey with these astroseismic results, and we got a target list approved, which is really marvelous, of about 10,000 objects in the apogee survey. Now, apogee is a beautiful instrument for this. The field of view of apogee is about 6 degrees. So to first order, a single apogee image corresponds to one of the tiles on Kepler. It's an almost perfect fit. The density of targets, about 230 fibers per field, is almost exactly what you want. It's a high-resolution H-band spectrum, resolution of about 22,000. And there are wonderful dedicated spectroscopists who have an automated pipeline, which means you don't have to pore over the spectrum for a year to get an answer. They do all that hard work for you, which from a theorist point of view is absolutely ideal. And so from this, you can actually then get information on the metallicity of these stars, the temperature of these stars, and combine that with the information you're getting from the light curves to be able to see if you can extract stellar populations information from this. And the result is, I think, quite beautiful. On the left-hand side, I'm showing you what you would have gotten for the first data release 10 stars. This is about 2,300 stars that we just released as of this last summer. And this is what you would have gotten if you took the parameters from the Kepler input catalog. These are purely photometric parameters. And you can see these kind of characteristic error bars you have in gravity and in temperature. Now, if you take the ASCAP spectra, of course, you can get a spectroscopic answer. The precision is higher on both dimensions, and you start to see that this population goes into focus. This is the red giant branch. You see an overdensity in here, which might be the core helium burning phase. And now when you switch to the astroseismic data, you can see the color magnitudes snap into focus. You see the first descent red giant branch here. This is the red clump. This is actually the red giant branch bump, where the hydrogen burning shell crosses a discontinuity that occurred on the main sequence that came from basically the remnants of main sequence burning that was dredged up. And this is actually the secondary red clump that corresponds to stars between 2 and 2.5 solar masses that actually are predicted to have a lower core mass and a fainter luminosity because they have non-degenerate helium ignition. So this was predicted by theory. You can see all of these pieces here. And now what we can do is we can paint this. This painting is not by region, but the blue stars are the stars that are predicted to have the oscillation pattern consistent with a core helium burning source. The red stars are the ones that have an oscillation pattern corresponding to a shell hydrogen burning source. And so you can see that these things are not only in the right place, but they have the structure appropriate for a shell hydrogen burning object. These things have the structure corresponding to a core helium burning source. And if I look at the masses, these are all masses between 2 and 2.5 solar masses, and these are all masses less than 2. So we now have a way of painting the core properties of stars onto field objects using this combination of the light series data, time series data, and the spectra, which is kind of a brand new capability we never had before. Now, if you look at this in other dimensions too, you can start to see these patterns emerging. In this particular case, what we've done here is we've taken stars and painted them by mass here, showing the expected position of different masses. And we've painted them by metallicity, showing the expected positions of different metallicities. Now, of course, we're looking at a set of models where both things are varying at the same time. So you would expect that there shouldn't be a one-to-one mapping. But sure enough, on average, the high-mass things are where they should be. They're hotter. The low-mass things are where they should be. They're cooler. And you can see the same thing is true with the metallicity. Metal-poor things are, in fact, hot, and metal-rich things are cold. And more to the point, this was not imprinted on these stars by the solution method. This is actually an independent result of this. So it's, again, an encouraging sign that we're on the right track. Now, I think what this means for stellar populations work is it actually has a lot of very deep implications. One of the things you have to remember is whenever somebody gives you a stellar isochrone, they've given you something where they've calibrated it on the main sequence against a very small number, a couple hundred fundamental measured masses, okay, in binaries. We now have, in this sample alone, more than 2,000 masses in stars with measured chemical composition on the giant branch. That means we actually have an empirical statement of where giants of different mass actually live in the HR diagram. And when people do studies of, say, unresolved stellar populations and external galaxies and the like, what they're doing is they're relying upon the accuracy of these uncalibrated evolutionary tracks, which we can now check for the first time. We can figure out where the stars of the different mass live. We can start to answer detailed questions about where they are in the HR diagram. And we can do this in a way, I think, that will have a significant impact on the absolute precision of stellar populations diagnostics. And this is all something that we can do with what we have now.
Do clusters not also provide an opportunity to link positions of stars in the main sequence to the giant under controlled conditions?
But they don't give you mass. And so in the case of the clusters, we don't. And the other problem is that clusters have a degeneracy with extinction. And so traditionally, we solve for the extinction of star clusters, but we can't actually simultaneously constrain the mass and the temperature in the same place. There's a small handful of clusters where we're lucky enough to have eclipsing binary stars in the cluster, and in that case, we can sort of assume that the masses are the same. But that's a shockingly small subset, a handful of open and globular clusters. Yes? This is related to the opacity in the envelope of the star. The structure of stars is such that metal-rich giants are intrinsically high in opacity, and they have to be large. Convection is relatively inefficient, and they have to be large to carry the flux. So this is actually a prediction of interiors theory that we can now test rigorously. Now, if we want to move from this kind of generic thing to a test of the specific masses and radii, we need to be able to have calibrators. And this is a case where we've actually been able to do pretty well. This is two sets of independent calibrations. And the first, what we do is we take Hipparcos parallaxes of stars for which we have astroseismic estimates of the radius. We take the parallax and the temperature derived from the infrared flux method, and that gives us a radius, and we can compare that with the astroseismic radius. The other thing we can do is we have stars with interferometric radii, and if we have interferometric radii, we can actually compare the radius from the interferometry to the radius from the actual astroseismic solution. And in both cases, we get answers that are consistent within a few percent. And this is actually an encouraging internal consistency check, because these are completely independent lines of evidence. Now, mass is much, much harder, and mass is the quantity that we actually really want to have. There's a very small number of cases where we have mass estimates in binary stars. For example, there's alpha Cen A and B. There's a few stars that people are studying in the Kepler field now. But for the most part, our masses are kind of indirect. So we only have a couple of pinpoints on this. One very interesting recent thing that we've done is we've hit upon the idea of using halo stars in this project as actually being independent tests of the mass scale. The logic here is we have this is the first release of about 9 of the 80 halo stars that we actually have in our field. And this band here represents the sort of astrophysical priors on the expected masses that you should have for halo stars. The idea here is we know that the halo is old. If the halo is old and it's metal poor and it has a close to Big Bang helium, you know that the mass should lie between about 0.8 and 0.9 solar masses. And then this band over here represents the thick disk stars, where we have a somewhat wider, but still not very wide range of expected masses. What these are superposed here, these are the inferred astroseismic masses for this sample. And you notice that those points are all above the line. In other words, this is a sign that the naive ways of estimating the astroseismic masses are coming in systematically too high in this metal poor domain. Now, when we drill in a little bit closer, it turns out that a lot of the width of this band turns out to be reflected in measurement techniques. That is to say, how one actually measures the astroseismic parameters turns out in this domain to influence the mass estimates. And this is an example of the sort of calibration work that we're currently doing to take these mass estimates and anchor them to a proper absolute scale. However, there's an interesting other way of doing things. This is actually taking a measurement of the mean density, this delta nu here. This is the x-coordinate here. And on the y-coordinate, what I've plotted is the G-mode spacing. This is the frequency spacing of the modes that tell you about the properties of the core. You may notice that this G-mode spacing has a very, very nice mapping onto the theoretical predictions. This is the points here. These are the points for the core helium burning stars. These are the high mass stars I was telling you about, the low mass stars. And the point here is I have in one measurement a proxy for the density of for the mass and density of the core. The mass of the core is a luminosity constraint. And so in effect, this thing here, this G-mode spacing, is telling me primarily about the luminosity of the star. This one here is telling me about the mean density, and I can combine these two things to a solution for the mass, which it actually then turns out to be an extremely good agreement with the inferred priors for the halo stars. Down here I'm showing you the 3 cases where we actually can use this luminosity constraint or the G-mode spacings, and the predicted masses all turned out to lie very, very close to the range that you would have expected old halo stars to have. And so this is an example of how we are now in the process of taking this raw data that I was talking about, these kind of raw scaling relationship predictions, and we're now taking them and turning them into quantitative predictions at the few percent level of the masses and ages of stars for bulk populations. So I think the prospects for being able to succeed here are extremely, extremely good. Now, at one level, I'm talking about actually taking this astroseismic information and using it to turn it into properties we recognize, masses and things like that. But there's other levels at which this works too. And another thing I'd like to be able to convince you that we can do in the last little bit is that we can actually start to address questions like the absolute abundance scale in stars. Now, to do this, you have to be able to go beyond the broad picture, kind of the broad overall structure I've talked about, and to be able to zoom in on individual detailed frequencies. And the basic idea is as follows. Let's imagine that I have, say, a star that has a radiative core and a convective envelope. I have a whole series of modes that are penetrating deeper and deeper and deeper and deeper in this star, and then I have one mode that crosses just above the convective boundary and the other one that crosses just below. The one that's just in the convective boundary has been living in an almost perfectly adiabatic environment. That implies that there's a very regular spacing in the modes. Now I cross over to one that's further on down, it's seeing a different thermal structure and there's a glitch. This is the exact equivalent of putting a bead on a string and having it rattle back and forth. It's going to change the frequencies. And so this is data for the sun showing this kind of glitch, this departure from uniform spacing, decomposed into 3 different features that we can identify. This small, long wavelength one is the glitch that's associated with the depth of the surface convection zone. Okay, so we can see that. These other 2 higher amplitude ones are the 2 helium ionization zones in the envelope of the star. So in other words, I can see the places in the acoustic structure of the star where helium is ionized. I can measure how much helium there is by the strength of that ionization signature. And I can measure the depth of the surface convection zone. These are all observables. They're observed to exquisite precision in the sun, and we're now actually seeing them in stars. Now, the first order effect is effective temperature here, but the second order effect is the metallicity of the star. The depth of the convection zone will change at fixed effective temperature if there's more opacity sources, more metals in the star. This is an example of this in the sun. This is the measured surface helium and the measured depth of the convection zone of the sun, shown here in the 1 and the 2 sigma circles. These are the predicted depth of the surface convection zone and surface helium that arise from different heavy element mixtures in the sun. This is the Asplund et al. 2005 mixture, the Asplund et al. 2009 mixture, the Kafau et al. 2009 mixture, and the Graves and Sauval mixture, both of these with relatively higher or intermediate oxygen. You notice that these latter 2 are formally consistent with the helioseismic constraints. These other 2 are not. This is the solar oxygen problem in a nutshell. And there's been a lot of ink spilled on it, but the point is that when we measure the surface helium and we measure the convection zone depth of a star, we're actually measuring proxies for the absolute oxygen and iron abundances that you're looking at. One interesting point in the sun that I think is less commented on, by the way, is that the iron abundance predicted by these atmospheres models is in incredibly good agreement with the seismic predictions within about 1 or 2%. So the absolute iron scale that people are using is actually remarkably in agreement with what we think. The oxygen is the controversy. And so if you then looked in these stars, you would see that if I can measure the depth of the convection zone in these stars, these are the predicted convection zone depths as a function of mean density, which turns out to be a better coordinate than temperature, for stars of different metallicities, and you can see that there's a very, very large signature here in terms of the depth of the surface convection zone. So in other words, if we can measure it to about this precision, which is about the observational figure, we actually have a measurement of the absolute metallicity of stars using just acoustic frequency information. In effect, abundances without spectra, which is something that I like to be able to do. It's kind of a nice cross-check on the absolute abundance scale. And we can probably measure this at a few tenths of a percent. I will be closing in with, I think, what is the single from the stellar physics, the single most significant and surprising new result from astroseismology, and this concerns the internal rotation of stars. In the case of the sun, we've reconstructed the internal rotation of the sun, and we find that we have a latitude-dependent rotation profile in the convective envelope. We have an almost uniform rotation in the radiative interior and thus strong coupling between the core and the envelope. So we would have thought, based upon this, that other stars would actually have a similar pattern, that the cores of stars are almost uniformly rotating, angular momentum is very efficiently exchanged between the core and the envelope, and this latitude-dependent pattern that you're seeing here represents the dynamo mechanism and magnetoconvection in operation. However, this is one point in time. It's an old main sequence star. We know that stars have a lot of structural evolution, so you might be able to ask if this property is itself universal. Well, in a couple of beautiful papers, people were able to demonstrate that we can measure the core rotation in red giants, and the cores do not rotate at anything close to the surface rate. This here is showing you this shell diagram. This is from the de Hovels et al. Paper. This kind of almost constant ridge line here represents the radial modes, the ones that have no interaction with the core. And sure enough, these radial modes have no rotational splitting whatsoever. All of these other modes look like they're visually double here, not because you're seeing badly, because they're all rotationally split. All of the core modes are rotationally split, so the core is rotating fast. The envelope modes are not rotationally split, and the envelope is rotating slowly. And so this is a really, really interesting astrophysical result. This is furthermore general. This is from a more recent paper by Paul Beck, by Benoit Masser et al., demonstrating that we now have core rotation rates for some 300 stars. Typical rotation rates of first descent giant branch stars in the core are sort of order 10 days. Typical rotation rates of more evolved core helium burning stars are something of order 100 days. And this is something that we are now working on. Ironically enough, we actually need some help from people who do spectroscopy, because we have core rotation rates but not surface rotation rates for all of these stars. So we have a complete inversion of the usual astrophysical problem, to where we have to guess how fast they're spinning at the surface, but we know extremely well how fast they're spinning in the center. From this, we actually can deduce some very, very interesting bounds on classes of models that can be done. And I'd like to stress that this applies across the entire HR diagram. This question about whether the cores of stars rotate at the same rate as the envelope is an important question for supernova progenitors. It's an important question for understanding mixing in stars, understanding the lifetime of stars, and things like that. So it's a very, very general topic. And the first thing we can do is we can run limiting case models. This is from some recent work I did with Jamie Tayar, to where if we believed that stars had a solar-like profile, to where they were kind of maximally coupled, you would expect the core rotation rates of these giants to become of order 1,000 days, years, very, very, very long. If I had them decouple on the main sequence, they could have rotation rates of order seconds. Okay? So there's an enormous dynamic range that's in principle possible for core rotation rates. This is the domain that occurs if you have no post-main sequence coupling. In other words, the cores stop talking to the envelopes just after they leave the main sequence. And that appears to be what's happening in these giants. It appears that the cores and the envelopes stop communicating with each other after they leave the main sequence. If you skip through, however, and then look at the other group, you have a bunch of these secondary clump stars I talked about. These are about 2.5 solar mass stars. They're core helium burning stars. They have a convective core, and they evolve from the main sequence to the giant branch with very, very little interaction. And the net result here is that these things are rotating at almost exactly the rate that they would if they were maximally coupled. So in other words, core helium burning stars with a convective core appear to have an extremely tight linkage between the core rate and the surface rate. Shell hydrogen burning stars appear not to be talking between the core and the envelope at all, okay, on the red giant branch. This was not predicted by any of the classes of theoretical angular momentum transport models. All the popular ones that you've thought about are probably not correct. This is teaching us some very, very deep lessons about the physics of angular momentum transport in stars. And so I'll close here. I was to leave some time for discussion. I was going to talk a little bit about rotation, but that's fine. Rotation's another lovely diagnostic. You could ask me if you care. And I think the first take-home message is we can now measure bulk stellar populations, things like mass, radius, age, and rotation. And we can do these in a population where we can do scientific experiments. We can choose mass ranges we want to study. We can study lifetimes. We can do this in a way, I think, that will actually open up many, many tools for stellar populations. Interiors models have always had lots of very strong predictions about these things. It's just that we've never had a place to calibrate or test them before. And so if you have things where you were interested in looking at, say, very, very small age differences between populations, fine structure, looking for signatures of things like helium, you can do it. There's a beautiful interplay between this and Gaia, because Gaia is going to give us beautiful parallax and distance information. The combination of Gaia data plus astroseismology should be able to yield information on chemical evolution and helium, extremely tight calibrations of masses, and then you can, in effect, use this to paint masses onto the whole field star population inferred from Gaia. It could be tremendously, tremendously powerful. The surface gravities are incredibly precise, okay? The absolute errors in the surface gravities of stars near solar metallicity are in the 0.01 to 0.02 dex level. That is not a typo, that is not a formal error, that's an error. Okay, that's a number I'll stand behind. In the halo star case, it might be as bad as 5%. My apologies. So it might be as bad as 0.03 dex or something like that in log G. You should take these seriously. This is a stringent test of model atmospheres theory. Other things are we have entirely new categories of observables. And I'd really encourage people to start thinking about how you can look at stars differently. Interiors models are making predictions about the core mass and densities of stars. If these don't line up with theory, we are missing things like heating and cooling mechanisms in stellar interiors. If there is self-interacting dark matter that actually can annihilate and produce a significant signal, it will change the core masses and these masses will be wrong, okay? We can test this. We can test the helium ionization, the surface convection, zone depth, and other things like that. All of these represent fundamentally new windows on how we think about stars. Rotation, similarly, provides a very different kind of way of looking at stars, a very different way of setting clocks. And we're now in a very privileged environment where we can make all of these tests for the first time. We're really opening up a very, very exciting set of windows on our understanding of stars and stellar populations. The last note I'll make here before I close is that this also has a lot of implications for our understanding of, say, planets. Because if we're trying to characterize the ecology of planetary systems, a precise knowledge of the host stars is also extremely important. We should be able to do this to get really lovely information on ages, masses, and other properties. For the host stars of extrasolar planets, I think we're very, very likely to see some very interesting patterns that emerge from these field-starred studies. So I'd like to thank you all very much for your attention, and I'd like to thank everybody who's participated in the work that I've talked about.
So, thank you very much. It was a very nice talk. So I'll open up for questions. Maybe it would be nice to first ask the more junior people to ask some questions. Please go ahead.
Would you expect the non-coupling and the coupling of the core hydrogen burning and core helium burning to be due to an efficiency of a magnetic dynamo in the core?
It may just be a signature that convective cores are extremely efficient at exchanging angular momentum with their surroundings. Because the shell hydrogen burning stars have a convective envelope and not a convective core. And so it may be a sign that that's operating. The alternative is actually a really interesting one, because if I took a very, very low order field, like a dipole field, in stellar interiors, I would expect very strong coupling at all times. So something has to be breaking in that on the first ascension giant branch in order to be able to explain that.
Why can you see G modes in other stars and not in the sun?
In the case of the sun, the problem is that the G mode frequencies are very, very different from the P mode frequencies. And if you think about it, a water wave is basically like a cork bobbing in the ocean, okay, so it's going up and down. And so if you're in a radiatively stable region, I take a fluid element, I knock it down, and it just bounces back up again. If I'm in a convective region, I kick an element up and it keeps going up. It's unstable against the Schwarzschild criteria. And that means that the waves are actually damped in convective regions. And so a pure G mode signal you would expect never to be able to see in the presence of a deep convective envelope, like in a giant, for example. And it's only the fact that the frequencies are commensurate with the P modes that makes it possible to see. So it's an accident of stellar structure. It's lovely.
This comment, measurements of the convection zone depth for a half or a handful of this?
There's Msun et al. Have claimed detections in about 20 to 30 stars, so that's the kind of sample for which we should be able to get precise measurements of the absolute abundances. And something else I'll add, by the way, is that the apogee spectra are going to be public. The first couple thousand are already public, and the remainder are open to anybody who wants to be able to download them from the SDSS server. We really encourage people to be able to come and use this data in all ways possible.
Would you expect different frequency patterns if you look in different wavelengths? onto a star?
These are white light observations. In principle, one can also look at spectroscopy as opposed to photometry. One of the things I didn't mention is although we have these beautiful detections in giants, we have very few detections on lower main sequence stars. That's because the background is actually very, very high. The turbulent background is high, and it's hard to detect these low amplitude oscillations in those stars. If you actually have a spectroscopic mission, such as the Danish Msun network, you can actually get much higher signal-to-noise measurements than oscillations in velocity space than in intensity space. And so if you wanted to make chromatic observations, like using spectroscopy rather than photometry, that would be a reason to do it. You can actually do lower main sequence stars.
Okay, so general questions. Let's bottom up.
You didn't talk much about the photometric precision that enables these measurements.
Okay.
Now, how much can a limp along Kepler do in the future, and to which extent does it remain hopeless from the ground?
That's actually a really interesting question. Solar-like oscillations are a space game. Solar-like oscillations are kind of 10 micromagnitudes, 25 centimeters per second kind of a thing, right? Very, very hard. Luminous giants are several percent periods of 40 days. You could do luminous giant oscillations from the ground, and in fact, they're detected in the Opal network. Because the periods range from minutes for the sun to sort of 40 days at the tip of the giant branch. And to me, that's actually a really interesting window, because you could potentially envision all sky luminous giant astroseismology from the ground with sort of millimeter-class telescopes. It's entirely possible. So it's a matter of what your precision is and what your time baseline is. The problem is they are stochastically excited, and so you have to wait for a while to build up signal to noise. But a while is a few years. It's not, decades or anything like that to be able to do. Ogle was able to do it.
The cause of giants will later become white dwarfs, and in
Yes.
white dwarfs it's well known that the rotation periods are very long.
Yeah.
It could be seconds,
Yeah.
but we observe hours up to even
Yeah.
days, months, and
Yeah.
whatever. Is that consistent with the observation that you have for the
Yes.
cause of?
Yes, that's a really interesting point. I didn't have time to do that. If you take those core rotation periods I measured and you extrapolate the white dwarf phase, you get a period of 1 day. 1 day.
1 day, okay.
Which is actually kind of comparable to typical rotation periods that one would see. So that suggests basically the proto-white dwarf does not talk to the envelope after the core helium burning.
So it must have obtained its slow rotation already before that period.
Yeah. If I did it from the first descent giant branch, it would be much faster. If I did it from the core helium burning phase, it would be about a day. And so what that says is basically once I leave that core helium burning phase, the core never talks to the surface again.
I didn't quite understand how you can disentangle the chemical stratification from the physical stratification of the sun.
In the sense of the dwarfs where you're trying to get the age estimate?
No, I'm wondering if you know the wave spectrum. You need to know the chemical stratification and the physical stratification.
Yes. So there is an age dependence to that. And what you take advantage of is that many of these modes are trapped in an envelope where the chemical stratification is very, very low. And so as long as you're in since most of the sun travel time is in the outer part of the star, where the chemical composition is nearly homogeneous, you're not terribly sensitive to the internal composition profile. What you would do is there's a handful of modes that do penetrate that deep, and you would use those to actually measure the central helium in a dwarf. So the idea is I can choose modes by the frequency where I know what the turning point is, and I choose modes for my analysis method that are in the chemically homogeneous outer layers of the star.
Coming to the abundances from astroseismology and looking at the solar abundances, from what I've seen, you would say that this now lasting for a couple of years discrepancy between the seismic and the spectroscopic metal abundance in the sun is basically resolved. Looking at the results of Kepler.
Yeah.
I would say that you want nothing to worry anymore.
No, I would would say that it's in the range where we can identify solutions. So in other words, if I take the errors of something like the Kepler measurement, I take the errors of the seismic measurements, they are consistent with one another. In fact, I would even argue, really, that if you just inflated the Aspinall errors a little bit to reflect the internal scatter in different 3D methods, they would probably be marginally consistent too. It would be sort of a 2 sigma level discrepancy, which is not the kind of thing I build a dramatic chasm. So there's a possibility of a boring solution where basically there's an oxygen abundance that's a little bit higher than the 3D models might prefer, and a little bit lower than the interior seismic models would prefer. Too bad, really. I would like it to be more dramatic.
Further questions? Lisa, still have a question?
So you showed us this beautiful plot that distinguishes when you have technology, the dwarf and the giant and real process. Do you come across anything that kind of looks weird in this kind of classification? Because you showed us a beautiful, the more non-good or the more mixed up thing. But is there anything in between where you don't have information yet? Or
Yes, there are interesting subpopulations, absolutely. And there better be. In other words, if there aren't, we're doing something wrong, right? We know that stars merge, we know that they do strange things. There are, for example, there's one lithium-rich giant in an open cluster with an anomalous astroseismic mass measurement. It has a strange surface abundance and a strange mass. There are a number of the red giants that we're seeing which have low L1 mode amplitudes. So in other words, in some cases it's very hard to see this mixed mode pattern in the background, and we don't yet know what the cause of that is. These are things that have unusual mixing patterns or things like that. So we've now just sort of laid out the terrain, and now we're starting to be able to explore whether or not we can actually see, say, merger products, for example, whether we can start to see evidence of stars that might be very different. So for example, if there was a spread in helium at fixed metals that was significant, we should start to see an excess scatter in the mass measurements at fixed temperature. It should resolve itself out. We should start to be able to see clues about the chemical evolution from that. We're looking very hard for the anomalies, and we do know that about 20 of these things are very fast spinning objects, probably merger products. So we are looking at whether or not they have unusual properties.
You would of course like to do all this great stuff on any star in the sky, not just on stars that happen to be in the Kepler field. So what are the prospects? Test, Strato, anything else on the horizon?
Well, there's a couple of things that you can think about. One of them is that you could repoint the Kepler mission, as you mentioned. The difficulty there is unless you're perfectly in the ecliptic plane, it just rattles around all over the place, and it's hopeless. But if you stay perfectly in the ecliptic plane, you have a chance of keeping it pointed stably enough to be able to do seismology. TESS is actually a wonderful mission, particularly for the dwarfs, and I think that TESS will actually provide us potentially a lovely yield, because TESS gives us 1-minute cadence data, which is perfect for dwarfs, for a number of bright objects. This will sort of give you seismology for sun-like stars. For giants, TESS is unfortunately only about 27 days long, so that means we're not going to get the luminous giants. We're not going to have a time series to do that. We will get the low luminosity giants at lower signal noise, so we will get that out of TESS as well. In terms of other missions, Plato would be lovely, in terms of being able to be designed as a wonderful astroseismology engine. And the other thing is, I think we have really not explored enough the upper main sequence. Kepler was deliberately targeted to make sure that it avoided all those pesky massive stars, right? All those messy, ugly, massive young things. They didn't want those. And so as a result, we never have had the chance to have photometric data of that quality in the massive star domain, where we know that there are these oscillators there, right? So we actually might be able to find something really interesting in the domain, red supergiants or things like that, if we actually had a mission that pointed at them.
So the upper main sequence are limited by data or by theory that is just not able to get parameters in the same way from those messy.
The biggest problem is that upper main sequence stars are not balls. They rotate fast. And if they rotate fast, that dramatically complicates the propagation of non-radial oscillations. So things like delta Scutis are theoretically hard. But there are cases like the slowly pulsating B stars where that's not the issue. There are slowly rotating, slightly distorted massive stars where you could, in potential, get very good pulsation data. And that could be really important for